So in this video, we're going to look at the gravitational potential. So we've established by now that all of these things work exactly the same as if we were dealing with a point particle. I could replace this sphere with a point particle and everything works exactly the same so long as we're outside of the sphere itself. But now we've kind of talked about gravitational potential before, and we know how to use it, but what actually is the gravitational potential at any point? We know how to use it, we don't know how to actually work out what the value is. What I mean when I say we know how to use it is if I give you this, in this term it's a sphere, so this particle's in this gravitational field generated by this planet now instead of some point particle. But again, we know that it's exactly the same so long as we're outside of this sphere. And we know that the energy change going from V1 to V2 is given by delta, the work done, or our change in energy, delta EP, where that's our potential energy, is just given by the mass of this object, which say has mass of little m, times by our change in potential difference, so where we end up minus where we started, and that's our gain in energy, our change in energy. Here it's a gain because we've gone from a lower potential energy to a higher potential energy. Remember that potential energies are all negative, so potentials are negative here and increase up to v equals 0 at r equals infinity. So we can use that, but we don't actually know what V2 and V1 are. If we're told the starting value for V1 and if we're told what V1 and V2 are, we can work out the change in energy, etc. And we've done that a bit. Or if we tell us a starting one and then how much energy we put in, we can work out where we ended up. But we can't just work out, given a radius, what the potential is. And that's what we're going to do now. So there's a very simple formula for it, and that's that V, where V is our potential at any point, radius r, again for r bigger than capital R, where r is our radius of our object that's generating the field. We see that V is just given by minus g capital M over r, where V is our potential, g is the universal constant of gravitation, m is the mass of the object that's generating the field that we're moving in, and r is the radial distance we're at. So we need to note that this isn't an inverse square law, right? So that this is different to the things we've been looking at so far, where we divide by r squared. But that's true for forces and for the field strength, but for the potential, we're just dividing by r. And that's all to do with the fact that these forces, the field strength, actually the gradient of this potential. So we're only dividing by r, so we're only inversely proportional to distance here.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.